So we completed up to which part? We completed up to the torque, right? And we understood about this lever, and we also did this rotation. So the next topic is the next topic, and today I will try to complete this chapter, right? So today only a few topics are. One is one we will talk about this center of gravity. Then we will talk about moment of inertia. What is that? And then we will also talk about this radius of gyration. And then we will talk about we will revisit, right? Or revisit rotation about a fixed axis, right? And in that, we'll understand about the kinematics of rotation, and we'll also understand about the dynamics of rotation. Dynamics of right. So, and then we'll see that what is the angular momentum, about a fixed axis, and conservation of angle. So we will do all these topics. Okay. So first thing, what is this center of gravity, right? So we have a rigid body, right? And this is the axis of rotation. And we have different, so let's say these different particles or constituent particles, they are situated at, let's say, R1, R2, let's say R3, R4. At all these distances, these particles are situated, right? And they all have, let's say, this one have M1G, this one has M2G, these one have M3G, and these one have M2G. So all these particles have gravity, right? So all these have some gravitational force acting in downward direction. So center of gravity is the point in the axis of rotation. So the point at which the total gravitational torque is 0, right? So if we calculate the torque due to gravity, which is tau 1 plus tau 2 plus tau 3, and so on. Let's say it is made up of n particles. So all these ones would be 0, right? So let's say this is R cross, let's say Ri cross Mi and G. Because G is same, so there is no I. And this is 0 at the center of gravity point. So that is called the center of gravity, right? And this is for a symmetrical body. So for a homogeneous symmetrical object or rigid body. The center of gravity is at the geometrical center or is at the center of mass. Right. So wherever there is the center of mass, let's say we have this bar. This is uniform, and it has a center of mass at here. Right. So this is the center of mass at L/2 distance. So this is the geometrical distance, right? Geometrical center. So this point would be the center of gravity if this bar is homogeneous and uniform, right? So center of gravity coincides when your gravity is not changing, and this is a very small rigid body, right? And this coincides with this center of mass. So that is all about this center of gravity. Here the torque, total gravitational torque is zero. So any question in the center of gravity, guys? Any question?
No, sir.
No, sir.
Then let us talk about what is this moment of energy. So before we do the moment of inertia, let us recall what are the rotational analogs that we have studied so far, right? What are the rotational analogs? So we have translation motion and we have rotation. So we have displacement and in here we have angular displacement, right? In here we have velocity, in here we have angular velocity, right? And we have in here we have momentum, in here we have angular momentum, in here we have force, and in here we have torque, right? And in the last, we have mass in translation motion. So what is the rotational analog of, right? So let us try to figure it out. Okay. So what is the rotational analog of mass? So let's say that we have a rigid body, right? And it is rotating with some velocity. So we know that velocity of one particle, right? Let's say this is V1. So this V1 would be related to, let's say we have this fixed axis. So it has a omega angular velocity. So this would be omega R1, right? Similarly, let's say if I write it for the ith particle, so this would be simply omega Ri. Is this part clear?
Yes, sir.
Yes, sir.
Okay, so if I write the kinetic energy of this particle, right? If I write the KE1, so that would be half m v1 square and m1, right? So this would be simply half m1 and omega r1 square. Okay, so this is KE1. And similarly, if I calculate the total kinetic energy of this rigid body, so total kinetic energy this would be KE1, sum of all the individual kinetic energy, right? So let's say particle 1, particle 2, right? And particle 3. So all these different particles, right? So we have all the sum of all the individual kinetic energy. And so this is half m1 v1 square plus half m2 v2 square plus half m3 v3 square plus half mn and vn square. And we know the relation between the linear velocity and the angular velocity, right? So this is half m1 and this is omega r1 square. Similarly, I have m2 omega r2 square plus half mn omega rn square. So I can see that this half omega is common. So let us take this as common and oh, there would be square, right? So if I'm writing v square, so that is square, so all these are square. Right? Because v square, so this is v1, so v square would be omega r2 square. This is omega square common, and this is how much? M1 R1 square plus M2 R2 square plus Mn Rn square. So I can simply write this as in summation form. In a simplest notation, I can write it as I equal to 1 to m and mi ri square. Right? So this is the total kinetic energy. And if I compare this with the translation motion, right? So if I compare this with the translation motion, this is half and m v square. So v square is how much? That is omega and square and r square. Or let me write it as right. So analog of velocity is omega, right? So which means that this is the analog of mass in the rotational motion, right? So this I call as moment of inertia. So this is summation of MIRI square. Okay, so this is called moment of inertia. And this is the rotational analog of mass in linear or translation. Okay, so in a translation motion, we have this mass, but uh, we represent mass in the rotational motion as this energy, right? This is the rotational analog of mass. Is that clear, everyone?
Yes, sir.
Yes, sir.
Yeah. So this is in the discrete form, right? And if I want to write it in the integral form or in the continuous form, so I would be simply r square and dx. This is in the continuous form or the integral form. Right? If we have a continuous system, then this would be the moment of inertia, right? And if we have a discrete system, then this is the moment of inertia. Okay, so you guys please note down from here. Okay, and yeah, derivation of all these different things is not important because that is not in the syllabus. So I will only calculate the moment of inertia of the ring, right? About the perpendicular axis, and then we'll just you guys just memorize the moment of inertia of the different one. So that table is given in the NCRT book, so just memorize that. Okay, quickly note it down, and then we will, yeah. So then kinematics. Before we do that, we understand about the radius of that. Yeah, whenever you guys want me to scroll down this, you guys. So always remember that if you have a symmetrical body and uniform rigid body, then center of gravity will coincide with center of. But these two are different, right? Yeah, whenever you guys want me to scroll down this, you guys please.
Finish, sir.
Sir, can you
Scroll down.
Yes, sir. Sir, can I join from another device?
Yeah. Okay. So you want to join from another device? Yeah.
Yes, sir.
Okay. Yeah. Of course. Yeah. Yes. Whenever you guys have noted it down, Yes, noted, guys.
Just 1 minute, sir.
Okay.
Second scroll. Done, sir.
Done. Okay, so yeah, please. Now. Done, guys.
Done, sir.
So now let us understand about movement of inertia of so you have a ring, right? And let's say this is df, and this is the axis of rotation, and this is r distance, right? From so this r is fixed, right? And this is so this r is fixed. So if you calculate the inertia, that would be r square and df, right? So this r is fixed, and you can take it outside, and this is df. So if you integrate it out, so that would be simply dm would be. So for ring, this is simply mr square. Okay, and that is so this is at the center, right? So you are rotating this ring at the center. So the center of axis is this center of this ring, perpendicular center. Okay, so this is the moment of inertia of the ring, and then you have different rigid bodies, and those are continuous. For all these bodies, you have to just remember what are this is table, right? Okay, yeah, and we can also see from here. So you have this object, right, and its position is changing. So it is rotating in this way, right? So
Yes,
it's
sir.
so for this case, the axis of rotation is not fixed, right? This is the axis of rotation. This is the axis of rotation. This is the axis of rotation. So in our case, for this simplicity, we will consider only those rotation motion whose axis of rotation is fixed, right? So all the rigid bodies that we calculate, so its axis of rotation. So that is the key idea. So for the ring, right, perpendicular to the plane, so this is mr square. But if we are rotating this ring diametrically, right? So this is the axis of rotation for the first case. But if we are rotating it diametrically, right, then the this inertia would be different, right? And because earlier it was used to be this perpendicular axis theorem and parallel axis theorem. So to calculate moment of inertia, but that is not that has been omitted. So that is why we are not discussing, right? So you only have to remember all these values. So for the case of the rod, right, and the center of axis of rotation is the center of this rod, and then we are rotating this rod in xy plane. So then the inertia is mx square by 2. Okay. So and for this disk, this is mr square by 2, which is same as this diametrical one. So you'll have to remember all these, right? So you have 8 homogeneous shape, uniform shape, and you guys have to remember all these values, right? So always remember these are important. Okay, so just note down this table at somewhere and remember the axis of rotation, right? So this is this is the moment of inertia, and there is this term which is called the radius of gyration. So let's say that yeah, so let's say that we understood that the moment of inertia of different object is different, right? So when we are calculating the axis of rotation and when we are seeing the moment of inertia of different objects, so so you see that this is mr square, this is mr square by 2, this is ml square by 12, right? All these values. So with these values, we define a radius of gyration. So what is the radius of gyration? So as this name suggests, what physical quantity is this? Radius of gyration would be what? What physical quantity? We have this seven fundamental physical quantity, right? So
Yes, sir.
radius of gyration would be what?
In 7 different fundamental.
Yeah, so you have seven fundamental units, right? Physical quantity, fundamental physical quantity, fundamental units, length, mass, all these things. So radius of gyration would be what in one of these? Is that velocity, intensity? Is that current? Is that what is that? Yes, is that time? Is that mass? What is the fundamental quantity? Radius. If I say radius, what is that?
Length.
Length, right? So that is length. So radius of gyration would be a length. Radius of gyration would be a distance. And what is that distance? So it is that distance from the axis of rotation, right? So we have this axis of rotation and we have, let's say, this ring. Or let me take this ring. So we are taking this. If I am drawing in this way, which means that I'm taking a diametrically, right? So I have this ring, I'm taking it diametrically. And I know that my inertia is mr square by 2, right? So, and this r is this length, right? This is the r. But I choose a distance, let's say k, at which my moment of inertia becomes the center of mass and inertia becomes the square of the distance. So I choose a distance at which the inertia becomes the total mass into the square of that distance. Then that k would be called the radius of gyration, right? So it is the distance from the center of axis of rotation at which my moment of the total mass and the square of distance. Is that part clear? Is this
Yes.
yeah? So let's say I want to calculate the radius of gyration for this thin rod of length L, right? So for the radius of gyration, my moment of inertia would become ml mk square, right? For the radius for this thin rod. And I know that moment of inertia of this rod is ml square by 12, right? Which means that if I compare these two quantity, then this length k, this distance would be simply L by root 12, right? So let's say that if I'm here and from L by root 12 distance, or let's say L by root 12 distance here, my moment of inertia at this point would become mk square. So that is called the radius of gyration. Is that clear, guys?
Yes, sir.
Now we can write what is this radius of gyration. And you guys, please remember all those value of inertia, right? So distance from the point of axis of rotation where moment of inertia becomes the product of total mass and the square of that distance is called radius of gyration. Right. So whatever inertia is given, right? If you want to calculate the radius of gyration of anything, so let's say you want to calculate the radius of gyration of a ring, and your axis of rotation is perpendicular to that. So you have this ring, right? And then you take the axis of rotation perpendicular to this plane. So we know that this I is simply mr square, which is this r. So if we compare this with this mk square, So your K would be simply 4 or 3, right? And we are taking the axis of rotation perpendicular to this plane of it, right? So whatever material or whatever rigid body is given, if you want to calculate the radius of gyration, so you just compare the inertia with mk square, and then compare I with mk square, and then calculate. So that would be simply your radius of gyration. Is that clear, everyone?
Yes, yes, sir.
Yes, sir.
Yes, sir.
Yeah. So please note this part down, and then we will. Yeah. So then we'll understand about the kinematics, dynamics, and lastly, we'll talk about the angle.
Sir, can you scroll down?
We note it down, guys, and we will. So I have question which is one very important, and I will give you guys some questions from the exam. You guys, please try. Yes, whenever you guys have noted it down, please.
Sir, can you scroll down?
Yeah, this part is also only this part.
Sir, 1 minute.
Sir, K will be root I by M.
K would be root I by M. Yeah, so yes, obvious. K would be root I by root M. And we can put all the values of I. So different objects, this moment of inertia is dependent upon the orientation, size, shape, axis of rotation, mass, all these things. So these moment of inertia is dependent on that. So we have seen the 8 different rigid bodies, right? So you guys please revise that table number 6.1 rigorously, and many a times just write it down, right? And remember what axis of rotation you are taking. Yeah, note it down, write it down many times, then you will be able to memorize. Yes, noted everyone.
Yes, sir.
Yes, sir.
So now let us talk about kinematics of rotational. Okay, so in a linear motion, what we usually did. So let's say we had this car, right? And it was moving with initial velocity u, and then we provided some acceleration, and then it was moving with final velocity v, and it had some constant acceleration, right? So these things we understood, and we wrote all these kinematics equations. So we wrote that v final velocity was u plus at, right? We wrote that distance was ut plus half at square, and we wrote that v square minus u square is 2a. So these things we wrote, right? and this was in the translation. But now what is happening is that you have an object which is moving in a circular motion, right? Rotational motion. So let's say you have this object and it is moving in a circle. So let's say it is moving and its speed has increased. So what speed is increased? Initially, it has an angular velocity w, right? And then you increase the acceleration. With constant acceleration, its angular velocity will increase. What do I mean by angular? Angular acceleration or angular velocity. So it is covering more number of rotation in some fixed time, right? So it is covering more rotation in a fixed time. So it has some angular acceleration. So then at some point, let's say at some time t, the speed, angular speed will increase to let's say w. So then correspondingly, what would be the kinematics equation, right? So we just take the analog and we write final velocity is initial velocity plus acceleration into time, right? So W naught is initial angular velocity or angular speed, right? What do I mean by angular speed? So how much angle it has covered, right? Let's say it is changing the angle, right? So in here, this angle is different, in this angle is different, in this angle is different. So it is covering different angles in particular interval of time, right? So that would be the angular velocity. So let's say it has some initial and angular velocity or speed when we are talking about the magnitude only. And then alpha is angular acceleration and W or omega is the final angular velocity or speed. Right. So if we write it in vector form, so that would be velocity. If we write it in the non-vector form, then it would be. So this is this, and similarly, what would be theta? This would be what, guys? Can you tell me?
Any angle?
So this is the angular distance. S was qt plus half a t square. So if we take the analog from here, what would be this? This is our u, this is our a, this is our v, right? In rotational analog. So what would be in here?
Initial angular speed or velocity
Yeah, omega naught.
into time
Yes,
plus half alpha into time square.
right. So this, yes, absolutely correct. So is that correct, everyone? Is that correct, guys?
Yes, sir.
Yeah. Similarly, the final thing. So omega naught square minus W naught square, that would be alpha and theta. Okay. So this is the kinematics. These three equations are kinematics of rotating object. Is that clear, everyone?
Yes, sir.
Okay, so I have told you guys about that, but can you guys tell me what is the difference between kinematics and dynamics? What is the difference? What is the difference between kinematics and dynamics? Both are study of moving objects, right? But what is the difference? Yes,
Sir,
guys.
one is during motion of an object, another one is at rest.
Other one is, which one is at rest?
Dynamic,
Dynamics. Then what is static?
static. Sir, you said kinematic, right?
Yeah, yeah. You are saying that study of rest object is dynamic, right? Then
Yes.
what is static or static?
0.
Statics is the study of rest object, right?
Yes, sir.
Yeah. Both are kinematics and dynamics. Both are the study of moving objects. But when you don't consider the cause of motion, right? Did we consider that what is causing these speed and acceleration to change? Did we consider that in kinematics?
No.
We just consider that something is happening and the velocity is changing. We are not considering that what is changing the velocity, what is happening with the system, so that it has gained some acceleration, right? When we study the moving objects without considering the cause of motion, then that is kinematics. When we study the moving objects, but considering what is causing the motion, then that is called the dynamics. So in the fourth chapter in laws of motion, we talked about the dynamics of motion, right? So what are the forces that are involved to change the motion of the object? So when we understand about the force, the work done, all these things, so that comes under dynamics. And when we talk about the velocity, acceleration, distance, right, without considering the force, then that is kinetics. Is that clear, everyone?
Yes, sir.
Okay.
Yes, sir.
Yeah. Then let us understand about dynamics of so in the case of the translation motion, we understood that the work done, small work done is simply F dot ds, right? Similarly, in the rotation, so this is the translation motion, right?
Yes, sir.
And the rotational analog of this, so rotational analog of this thing would be how much? So the work done due to the rotating force. So what is the rotating force? What is the rotational analog of force, guys? Rotational analog of force. That is why this table is important.
Torque.
Yeah, so alarm is saying torque. Torque, right? So the work done in the case of rotating body, that would be tau d theta, right? So this is the work done. And if we write and you guys have already seen that what is F equals to ma. So this for the case of rotating body, that would be what? What is the rotational law of mass? Yes, rotational law of mass. Phi. Rotational law of acceleration, that is alpha. So this would be in force, right? And similarly, what would be the kinetic energy? Or if I write what is F equals to dP by dt, right? So for the case of this torque, that we have already done. So that is dS by dt, and this is external, right? Okay, and the last one, which is the kinetic, so we have half mv square, and for the case of the moving rotating object, that is half m is I and v is so these are the rotational analog of dynamics of rotating object. Is that clear, everyone?
Yes,
Yes,
sir.
sir.
Yeah. So then please note down this part, and then we will understand about the last topic, which is rotation about a fixed axis. And then we will see that what are the components of the angular momentum, and then we will again understand about the time conservation of angle. Those are things. Whenever you guys want me to scroll down, please. See, this chapter will be completed, right? And tomorrow I will quickly complete the half portion of gravitational, gravitational force, right? And in the second book, so the second book, all the chapters are small. First one is this mechanical properties of the solid, which have stress and strain. So those are only a few very small chapters. Only this fourth, fifth, and sixth. These were the headings, right? So you guys concentrate on first 7 chapters, and then you guys can score major portion of the syllabus is first 7 chapters, right? You guys revise those portion, and when I complete all these chapters, I will revise those portions. Yes, noted everyone.
Finished, sir.
Okay, then
Done, sir.
yeah, please write down. Right, so there was these derivation which are not that important. So I have just skipped those, and I have just skipped. You guys have to just remember, in kinematics we have to write all this equation. In dynamics, we talk about the force, external torque, or all these. Right.
Finished, sir.
Okay, so then let us talk about the angular momentum about a fixed. So to do that, let us quickly go back to what we got for the case of this So how did we get this equation? Let us go back, right? And then there would be, we have, let's say we have an object which is moving in circle, and this is the axis of rotation, right? So let's say this is the velocity, right? Or let's write a 3D representation. Let's say this is unity. This is into this, right? How should I? Tangential, right? This is going in this direction, right? And then I have this position vector r of this object at this is my position. This is my r. Let me write it as O. This is P. And this point is the center of, right? And this is the axis. Okay. So this is this direction, this is this, and we want to calculate so we want to calculate this omega velocity. So we know that this is the omega velocity, right? So this perpendicular direction is this is v. So if we want to write what is this, if I want to calculate what is angular momentum, right? So that would be R and cross B for this object which is moving in a circular direction, right? So this R vector is OP. And can you guys tell me that what is this distance?
R.
Yeah, so this is the R, right? And this is the perpendicular distance. Okay, from this point, this is the perpendicular. Clear?
Yes, sir.
Yeah, so if I take this omega is in k hat direction and this is r perpendicular. So if I write OP, okay, this is my vector. And you guys have to remember that what would be this vector. So what would be this OP vector? Using the property of the triangle. We just did in the previous class, right? Earlier class, Rishita and Alfred. What would be this
Yes, sir.
OP vector? Let's say I have this vector and I have this vector. This is A and this is B. So I want to find out this vector, right? This would be what? Resultant A plus B. This is the triangle's law, right?
Yes, sir.
So I am going in this direction and then I am going in this direction and I am going in this direction. So this OP would be OC plus CP. Am I correct, guys?
Yes, sir.
Yes, sir.
Yeah. So let us write that part, right? So L would be this OC plus CP, right? And cross P. Okay. So then this would be how much? So then this would be, let's say, this is And as Akib said, CP is what? R perpendicular, right? So this is CP cross P plus OC cross P. Okay. So CP is R perpendicular and its direction is what? Its direction is I hat, right? Its direction is I hat, velocity is in the direction of J hat. So this would be, this is R perpendicular I hat, and this is mass, and this is V and J hat, right? Plus OC cross. So then this would be how much? So this would be R perpendicular MV, and I cross J is K hat, right? Plus OC cross. Okay. So I can write V as omega R, right? So this would be M R square and K hat plus OC cross P. So this is what direction, guys?
Positive.
K hat. What is K hat direction?
Perpendicular to I and J.
Absolutely right. Perpendicular to I and J. So what is that direction? K hat is what direction? What axis or whatever you want to call
Sir, like how you are asking?
it. So I hat is what direction?
I had x-axis.
X direction, right? So K hat is what
Yes.
direction? Yes, K hat is what direction?
Minus xy.
K hat is Z direction, right?
Okay, yes, sir.
K hat is Z direction. So P is omega R, right? So omega and R square. So this is, I can write LZ, and I can write this as L perpendicular. So I can divide my angular momentum in two parts. One would be in the Z direction, and the other would be the perpendicular direction. Right, so perpendicular to, so L will have two components, Z component and perpendicular component. So this is what I wanted to derive, right? In a fixed axis, angular momentum has two components. One is Z component and the other one is this perpendicular component, right? So this is the perpendicular component. This one is the perpendicular component, and due to this R perpendicular, there would be this Z component in Z direction. Okay. So I can always divide my angular momentum into parts. And for the case of this, so for the case of symmetrical rigid body, right? So for the case of symmetrical rigid body, let's say you have this object which is going in this direction plus V. So in the opposite direction with the same distance, you will have another V which would be in negative direction. Is this part clear? So this mass and this mass. So this is going in the positive direction, this is going in the negative direction. So L perpendicular will cancel out, cancel out in symmetrical rigid body. So angular momentum is just the contribution of z component. Is this part clear? In a fixed axis, of rotation, only the z component will contribute to the angular momentum. The perpendicular component of angular momentum will cancel out. Is that clear, guys?
Yes, sir.
Yeah. And we have found out that what is this LZ component? So LZ component was m omega r square, right? So m omega r square, and we know that mr square is I. So LZ would be simply I. This is the angular momentum of a fixed axis of rotation. Okay. And
Yes, sir.
you guys can also see from the rotational analog that linear momentum is mass into velocity. Similarly, the angular momentum, z component, that would be I, and this is for fixed axis of rotation. But if your axis of rotation is changing, then this would be different, right?
Yes, sir.
Okay, so from the last topic, which is conservation of angular momentum, right? So again, we already know that total torque, right? This is dF by dt. So if your external torque is 0, then your dL by dt, this would be 0, which means that L is constant, which means that Lz would be I. So which means that omega is constant and I is constant. So Lz would be I. So this is the conservation of angular. So any doubt in these portion, guys? Any doubt?
No, sir.
No, sir.
No, sir.
Move down this part. And my drawing is bad, so you guys can see this drawing in right. Guys can want to draw a beautiful diagram. Guys can see this drawing here. So this is the actual method, right? This is in the y direction. This is z direction. Okay, and this is the position vector, and this is the point of that particle which is there situated, right? This is rotating in this direction, circular direction, and the tangent to this one, right? Tangent to this one will give you the velocity, and this position will have two parts, right? So this vertical part and this also. This is the time. Okay, you guys quickly note it down, and then this chapter is right. And if I have missed anything which I didn't talk about, so you guys can point it out. This is the angular. Right. Idea of this angular momentum of a fixed axis is that we can write the angular momentum in two parts. So that is the whole idea of this fixed dynamics, right? So the object is whenever you guys want me to scroll down, guys,
Finished, sir.
and remember we have written it for one particle, right? So for all the individual particle, right? So this would be simply Lz would be mi ri square, right? Summation, and then this would be I, right? Yeah, whenever you guys want me to scroll down, please.
Done, sir.
Done. And summation of mi ri square. This part is why in symmetrical rigid body L perpendicular will cancel because you will get some term which is whose velocity is in this direction, and in some object this would be in the opposite direction. So these two will cancel out. So L perpendicular will cancel. Okay, guys.
Yes, sir.
Quickly note it down and then we'll do one question. We have 3 or 4 minutes, so we can do one problem. That problem is very important. So whenever you guys have noted it down, please.
Done, sir.
Then everyone noted.
Yes, sir.
Yes, sir.
Yes, sir.
And you guys, please do all these, whatever we have done. So if you practice these questions, and then you will understand, right? This question, that question, not this. The kinematics question. This one we have done. 6.11 and yeah, this one also 6.12. So if you guys will do these 2 problems, then you'll understand whatever we have done. But yeah, so we have to do this problem. 6 point, right? And we have these two. Walls and some string, and with this string, this bar is. Remember, this is a non-uniform bar, right? So its center of gravity would be different. So we have to calculate the distance d of the center of gravity of the bar from its left. So we have to find this d, right? And this is the weight of this object. This bar length is 2 meters, and this angle is 37 degrees. This angle is 53 degrees, and yeah, it's only okay. So I will write the things, right? So how many equilibriums could be there for this case? How many equilibrium, guys? Yes, guys, how many equilibrium could be there?
2.
Right, so one would be translational, because this bar is at rest, right? Which means that all the forces are balancing each other. And the other one would be rotation. So keeping this in mind, and you guys tell me that what are the forces. So this is a string. So first force would be, let's say, in this side, because the angles are different.